Hello students. In the last two lectures, we discussed the two very important experiments which really changed the science, which laid the foundation of entirely a new framework in physics, that is quantum framework. Now, let's move on. We'll try to see one more experiment with which you all are very much familiar with. Okay, so let us start with again the interference phenomena, which we have already discussed in wave theory of light, wave nature of light. Yeah. So in the most basic experiment which we discussed in interference was Young's double slit experiment. So let us start with that. So once again I start with Young's double slit experiment. So what we saw in wave nature of light, that in Young's double slit experiment, if I open one slit and close another one, for example, if I open S1, I get a pattern like this. This I'm drawing the energy. Okay, so you can imagine this as x-axis and this is as y-axis. So this is the height. Okay, and if I open the second slit, then I get a pattern like this. If you want to do the Young's double slit experiment in detail, you can refer my lectures, previous lectures on wave nature of light. Okay, and then we saw that if I open both the slits classically, or what should I get? That till here, before Young's double slit experiment, I don't know anything about wave nature of light. So I just know that light travels in a straight line, and then as I make the slit smaller, the light bends. Okay, that could not be explained. This bending of light was not able to explain by geometrical optics. So now when I reduce, and after that when I open both the slits, I expect a pattern with when the two patterns graphs will join. But what I got? The pattern like this. This is interference of light, and this can happen only when light is a wave, because classically also we know that when the two waves to superimpose, they interfere, and I get a pattern which is both constructive and destructive. So I get interference of light. This experiment proved the wave nature of light. Now this was well accepted by the world by this experiment. Then later on, a lot of experiments were done for diffraction, and we have studied all those experiments. Wave nature of light. Now I want to do something different. This was established, the wave nature of light. Now I want to go further. What do? I do the same experiment but with very, very low intensity. Then what do I expect and what do I get? We will try to see that. So now what do? I do the same interference experiment with very low intensity. Now with very low intensity. So for example, if I open both the slits, I know that I will get an interference pattern. But for example, what I do, I reduce the intensity to very, very low. What do you mean by that? I make my source dimmer and dimmer. This I can do by taking the source far away, dimmer and dimmer, so dim that on the screen it illuminates only 1 pixel. So dim. So what do I observe? What do I expect first? If I make my source very very dim, again I should get a wave interference pattern, because light is a wave, and I should get an interference pattern of very very low intensity. But if I do such thing, what I get on the screen is the spot. So that this was a very different observation. This was really surprising, that if I make my source very 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 dim, then I get, instead of a very dim wave or interference pattern, I get spots. What does it mean? What is the interference? I get spots on the screen. And when the energy and momentum of these spots were measured, they came out to be same. Spots were measured. It was observed that the energy of the spot was h cross omega, and the momentum was p is equal to h cross k, and the energy of all the spots was same. Now what does it infer? This was entirely a very nice result. It showed that light, which we thought of as a wave, is actually made up of particles. Light is made up of packets of energy and momentum, made up of particles called photons. Photons were not discovered by this experiment, but they were done by a different, which we have already discussed, that is photoelectric effect. But we got the same result, that light is made up of packets of energy, photons, particles called photon, and the energy of this photon is h cross omega, and the momenta is h cross k. Now from these two equations I get that energy is equal to P into C. From equation number 1 and equation number 2, I get, from equation 1 and 2, you can substitute that omega and k are related by C. If I compare this equation with relativistic equation of energy, this with the expression of energy as E square is equal to P square, this I can cut, P square C square plus M square C4. I can also rub this so that it is not confusing. Okay, so I will just rub this. Okay, so what is my expression? My expression is E square is equal to P square C square plus M square C4. Now when I compare this equation with this equation, what do I get? That these particles, this will be satisfied only when the mass of the photon is 0. When these photons are massless. So another very important point to note down here is that the particles instead of being massless, they can possess momenta only when, how they can possess momenta. So the particles being massless can still have momenta only when they travel with speed of light. Only when they travel with speed of light. This I can see speed of light. This I can see from the expression of momenta m is equal to mass into velocity, relativistic expression 1 minus v square by c square. Okay, this can be easily seen from this expression. Okay, so they can have, when the velocity of the particle, it travels with the speed of light and it is massless, then the momenta it can possess. So now I got a very nice result, that the lights which we thought was a wave is actually made up of photons. Light which we thought of as a wave is actually made up of photons, whose energy is E is equal to h cross omega and momenta is h cross k. This was a very nice result, and it again confirms the quantum nature of light. Okay, from this observation, there was a physicist known as de Broglie who made a remarkable observation. We'll try to see his observation in the next lecture. Thank you.